And a link will be sent to all the participants, in a follow-up email that we will send out after the webinar. Also, attendees will be muted. Okay, so please use the chat to ask questions, and at the end of the webinar, we will cover these questions between Dale Schick and myself. Both Dale and myself are application engineers with many years of experience helping customers solve testing problems. So now, without any further introductory comments, let's proceed with the live webinar. So the agenda for the meeting will be in two parts. Dale Schick will be doing the part with the focused on vibration control topics. Obviously giving some background on vibration control, the external and software summing, force limiting configurations, notching techniques, and certainly a live force limited demo, which is really pretty cool. On the other hand, I'll be talking more on the force instrumentation topics. Why force limited vibration? What about multi-component force measurement considerations? How do you measure forces in moments? And brief application example. So it's always good to, I think, start out sometimes with just the overview. Satellites and payloads undergo a real aggressive life, during launch and deployment. And you can see here this author who wrote a very good article on environmental testing. So it shows the various launch events, separation events, and so forth. And you can see the various relative levels of vibration and shock and so forth that the payload has to endure. So the whole area of environmental testing is very important in ground test, to ensure that you have an operational ready satellite. Considerations and testing includes components, subsystems, and payloads, and spacecrafts and payloads. So you're looking at all several types of vibration testing, whether it be sign, random, transient, modal analysis, force limited vibration, shock testing, vibroacoustics, electromagnetic, as well as thermal vac testing. So as an example, just as a bit of a motivation, there was a satellite glass mission that basically was instrumented, specially prepared with force sensors and accelerometers to try to quantify the level of vibration and force that was present during launch and flight. So the first plot is a really example of acceleration over frequency. You can see some peaking of around, a quarter G or so at the lower frequencies. And you can see the first axial mode of the spacecraft is around 32 hertz on the force plot. And then the lower frequencies are caused by the launch vehicle, where you can see upwards of 6,000 pounds of force, at the axial mode, as an example. So you can imagine that there are considerable levels of vibration and force that the test article or the satellite is undergoing over launch and flight. So the vibration test problem can be illustrated with this slide. The dotted line is an in-flight acceleration at the interface, and there's a load anti-resonance where the acceleration is reduced, but the force is increased. So a standard vibration controller would increase shaker output, resulting in overtesting for this condition. And the overtesting could be up to, say, 20 dB. So force limited vibration helps to solve this problem of overtesting. And that's what we're going to talk about a little bit. So in terms of the setup, traditional slip table, and you see a test article with a force ring or with a ring, and then multi-component force sensors measuring the fixed base resonances of that test article. The setup includes 3-component force sensors, dynamometers, head expanders, data acquisition systems, and so forth. So it's fairly complex setup. So in terms of this, the force limiting really replicates the test article resonant response for the actual flight mounting condition. That's really the objective. So the flight equipment is typically mounted on relatively lightweight structures, which have similar mechanical impedances, where shakers, on the other hand, have near infinite mechanical impedance, and that's the issue at hand. So traditional vibration testing response limiting, controls the input acceleration to the frequency envelope that we showed. So limiting on this test acceleration responses is typically very analytical in nature. So what happens is when you're limiting the input force at the fixed base resonance of the UUT, it's less dependent on the analytical models and provides an automatic notching without over testing. Now, Dale's going to give a real good example of this during his session. So about automatic notching and also manual notching and contrasting the two. Obviously, the control system is an extremal control. So conceptually, at frequencies other than the test item resonances, the acceleration test specification usually controls the test level. However, at the resonances, the base reaction force is increased, and that's where you want the force control specification limits on the input force. So not to overtest the satellite. So here's an example of what that might look like. In this case, you have an unlimited input force, which you can see peaking outside that enveloped condition. And what the force limiting would do is put a very sharp notch, approximately the mirror image of that force peak, and that would tend to bring it all into that envelope of test. So not to overtest the payload. So now let's just go into piezoelectric instrumentation. This presentation is going to be mainly talking about force, although acceleration is a very important measurand as well with force limited vibration. But with force sensors, we're talking sensors that can measure three components, X, Y, and Z. And oftentimes we talk about devices called dynamometers or force dynamometers, which in this case here shows 4 of these 3 component sensors comprising this force dynamometer. So these force dynamometers actually can take many different shapes, and you're going to see some during this presentation. So some terminology: piezoelectric and IEPE. I mean, IEPE means all those trons like piezotron, deltatron, isotron, and so forth. All those trons, ICP, and so forth. So they're all meaning IEPE sensors. There are trade names of various companies, trademarks of various companies. With IEPE, you have electronics inside the sensor. Excuse me. And with that, basically, you're limited to the range. You don't have rangeability. So you have a fixed range, fixed noise floor. The good news is many data acquisition systems have the capability to already have this constant current supply to power it. So from an integration standpoint, it can be quite handy. Also with these sensors, it's mainly for dynamic measurement, and doing quasi-static or required for preloading is often quite a challenge because of the dynamic nature of the sensor. With regard to piezoelectric, on the other hand, the electronics is outside, so you have full control of rangeability. You have full control of quasi-static, so you can create ranges that complement whatever your preloading might be for the force sensor. We're going to talk about preloading. It's a very important part of installation of 3-component force sensors. And obviously with this technology, with piezoelectric, you also basically get a tear of the system with regard to the static mass. So your dynamic range is really represented by the dynamic nature of your test, which is, I think, a good utilization of your dynamic range. So in terms of a piezoelectric sensor, I mean, you typically talk about them as a lightly damped second order system and a single order high pass characteristic on the low end. So because it's the lightly damped second order system, you can often write closed form expressions which help to estimate what might be the amplitude response of your vibration fixture. So if you know the natural frequency of your vibe fixture, you can estimate the 5% amplitude response would be Fn over 5, 10% is Fn over 3, and the 3 dB would be Fn over 2. So on that basis, a lot of times these charge amps that I talked about, these external charge amps, very vital to being a flexible means of adapting to various vibration fixtures and various payloads. So you have almost one size fits all type of approach. So what's often notable with charge amps, they basically take charge and convert it to a voltage, typically plus or minus 10 volts. And typically what you like to see is a wide measuring range. Charges in picocoulombs, 2 to 2 million is a pretty capable amplifier. It can take on almost any challenge out there. Wide bandwidth of the charge amp as well. The charge amp is not the limiting factor to frequency of your measuring chain. It's really the vibration fixture. So I won't spend a lot of time on the low frequency side, but fundamentally it's dictated by the time constant of the charge amp. And what you see is the low frequency characteristic is actually a function of measuring range. And what happens is that when you get into dynamic testing, you're typically working with short time constants. So your frequency, your low frequency is effectively AC coupled. When you're doing preloading functions, where you need, where you need a quasi-static capability, you would be using the long time constant, which really enables you to measure very accurately preload forces, and which is a very important step. So just as a say a visual illustration, dynamic charge amps, I mean, are ones that will measure transient events, sinusoidal or random events, and certainly they're not optimum for measuring these static events. However, quasi-static charge amps could measure everything dynamic as well as this static measurement. So such as preloading, for example. So just to illustrate on the point I made with rangeability of the measuring chain with an external charge amp, I just wanted to show here you have a 10 kilonewton sensor and you're ranging it for down to 1 Newton, for example. And you can see the broadband noise, which would be like 1 to 10 kilohertz, actually reduces with ranging the sensor down. This is actually quite powerful because the noise voltage of the amplifier is just allocated to a different measuring range. So it's really a powerful way to get high resolution even at the lower ranges using one sensor. So there's other amplifiers that often come into consideration when you're looking at a force limited vibration measuring chain. They could be quasi-static amps, such as these that have both quasi-static amplifiers and integrated data acquisition on top. And then you also have dynamic amps, such as the one below, which also has the ability to do IE, PE, charge, and have a data acquisition there on top. So sometimes it might be of interest to have a backup data collection, for example, and such devices would be a bit able to do that. So as I said, with these devices, it's rangeability. You can, because they're high channel count devices, you can literally put each channel of your force sensors into the controller and let the controller do the calculations there, which is a lot of times the preferred method. So when we talk about force dynamometers, and a lot of times there may be some that are available off the shelf, and in most cases for force limited vibration, there's a lot of customization at the given company. So they have certain payloads, they have certain test requirements, and they're able to now take these 3 component force sensors and use them as modular building blocks to create different shapes and sizes. It could be circular, rectangular, triangular, rectangular type of dynamometer plates that basically will, because and the reason why you use dynamometer plates is because you don't typically have an axial force when you're testing these large satellites. You have a distributed force over a larger footprint. So with that said, you want to be able to, if you use a single sensor, you wouldn't have the right measuring instrument. It would possibly break or give you very much a poor result because of the bending moments involved. So the dynamometer itself will absorb moment loads by differential force reactions within the sensor array, and whether it's 4 sensors or it could be 16 or even more in some of the installations, it's all based upon the same concept. It's always important to remember the analog bandwidth considerations of your test, and the analysts will know what frequencies are of interest and what the test regime needs to be, and that's flowed down obviously to the test folks. So the vibration fixtures need to obviously be stiff. You need to have natural frequencies that are consistent with whatever test regime is of interest. So having stiff force sensors between parallel plates, like I'm showing up here, which is a dynamometer, parallel plates, force sensors, really gives you the basis for making a stiff vibration fixture that can handle the various frequencies. We're going to talk a little bit about how to do that and what are the general rules to consider, and that's coming up shortly. So just to sort of highlight what a force sensor might look like, these are 3-component force sensors, and they're at various, say, capacities, load handling capacities, and sizes. But the sensitivity is roughly the same for these sensors, but there are some special cases where different materials might be used internally. But what you like to see here is that if you look at the stiffnesses, there's axial, shear, rotational, and bending stiffness are clearly defined. So from an FEA standpoint, you can easily model, CAD models would be available. You can easily model this within your vibe fixture and really understand what the resonance capabilities are, what the frequency capabilities are. And you can see here, these sensors would require a preload, which we'll get into. And these sensors here are called force links, and they would be already preloaded at the factory. What happens is you gain height, usually 2 to 3 times the force sensor, and you lose stiffness because of the construction. So in this case here, if we just took the 9367, I mean, that, say 4,000 newtons per micrometer, and the sensor itself would be almost double that. So going to force links, it does simplify the installation, but in general, a lot of the satellite testing uses still the individual sensors with a preload, but there is a mix depending on the application and needs of the test. So there, both can be used, but I'll say we still see a fairly high usage of the force sensors because of the attributes I mentioned. So this is what a dynamometer, a simple rectangular or square dynamometer might look like. You have 4 3-component force sensors. That's 12 signals total. You have an A separation, which is the separation from the center of the sensor to the center of the dynamometer. And you have a B, or vertical separation is A, and the horizontal separation is B, which is from the center of the sensor to the center of the dynamometer. Now, without losing any capability, we're able to pre-sum and charge internal to the dynamometer to take 12 signals and output them to 8. And these 8 signals, because of geometry, you can easily write the expression, the 6-component expression, all the forces and moments, which you can use. You can use the moments for computing, say, overturning moment, for example. A lot of times in the more modern systems, you have the vibration controllers are very capable to, such as the Vibe Runner, very capable to compute in real time all these calculations, all these equations, and all you have to do is put in the geometry, and it's off and going. So, so that's an important note. So if you really want to do the math instead of letting maybe the M+P system do it, this is the way it would be done. You would basically take the geometry, you group sensors in pairs about a given axis, and then you'd simply write the expression of the moment given the horizontal moment arm or the vertical moment arm, and then you would just simply write the MX, MY, or MZ expressions, and that's basically how it's done. In larger dynamometers or with more sensors, the calculation is basically the same, and we'll go through that in an example a little bit later. So here are some multi-component force basics. Load-bearing surfaces are very important. You want surface Flatness and parallelism, that's very key to getting good frequency response. You certainly want strength of materials. In terms of preload, this is probably the most important step in terms of installing sensors, okay? And what you see here is you see a ring nut, see a bolt. In the middle, you see an isolation centering sleeve that also isolates the sensor from the ID of the force, or isolates the bolt from the ID of the sensor. And basically what you also want to note is the actual force sensor has a ceramic top and bottom plate on and what that does is it does two things. It increases the frictional coefficient from a 0.1 to a 0.2. That then will actually increase your shear force handling by a function of whatever the preload force is times the frictional coefficient. And it also provides ground isolation, which is always a best practice when you're doing high fidelity measurements. Also, preloading optimizes linearity and stiffness. You're usually preloading to about 70% of the full scale range of the sensor. It also provides compressive and tensile force handling symmetrically, and I'll show you an example of that later. And the shear force handling, as I just mentioned, to eliminate any slippage, possibility of slippage. Linearity is basically the input versus output through zero, and you then compute the deviation to that straight line, and that would be the linearity. Oftentimes with piezoelectric sensors, you're able to do partial range calibrations, which give you the ability now to dial in a specific sensitivity and actually improve linearity in most cases, where you can see in this case, the full scale range of the sensor is 0.5%, but if you go to a partial range of 10%, you're at about 0.1% linearity. So you can see by taking care and doing a partial range calibration, you can optimize your setup for the best linearity as well. Shunt preload bolts creates a shunt force, and typically the bolt takes up about 6 to 9% of the force, which means your sensitivity will be 6 to 9% lower because of the bolt. That's all very important. So I often get asked the question, hey, can I use my own bolts? And my answer is always, well, the bolt has to be capable enough to hold to deliver the force that you need for preloading, but it also needs not to be so stiff that it actually takes up more of the force, thus reducing the sensitivity of the sensor. So you need something, say an engineered bolt. You see here a tensile and compressive force. If you preload at 2/3 of the full scale range, you're able to get plus or minus 1/3 for compressive and tensile force measurement. So it gives you an example why preload is important, is because you also get compressive and tensile force handling. Alignment of sensors is critical. Every 1 degree of misalignment is 2% of crosstalk between X and Y. Crosstalk is basically illustrated here, in this case, FX to Y and Z, or to X and Y between each other, and X and Y to Z. So you can see these would be like data sheet values, but you can see the actual calibration sheet values are substantially lower, which is very accommodating to more accurate testing. So in terms of preloading, I just wanted to mention, sometimes people will use these cylindrical pins near the connector of the sensor to keep it from spinning during preload. Now, more innovative Vibe Labs will build a fixture with adaptations, which will allow a pressing piece of metal against the flats of the sensors to basically hold them in place. And then after all the preload is done, you simply take out the socket head cap screws right here, and you're left with just the Vibe fixture. The adaptations go away. Really innovative approach here by this Vibe Lab. So just to talk about a little bit about preloading. With preloading, when you have multiple sensors, it's just like putting on and changing your tire. You don't torque down one bolt all the way and then hope for the best. You do a star pattern. And with preloading, because it's so important, you want to create a sheet that talks to each step. So you might do this in 25% increments. If you have to preload to a certain value, you go 25% in the star pattern, then another 25% in the star pattern, and you initial each step. And that way you can't get confused. If someone pulls you away, you always know where you were in the preload arrangement. So that's a very important point. And in this case with preload, your system would be a quasi-static measurement. You'd be measuring the FZ, and you'd be making sure it's within the design limits of the manufacturer. Mention again here, dynamic model with dynamometer. It's a spring mass system. So, the simple equations that I showed to the right are very applicable. And what you see here is when you add mass or reduce stiffness, you're going to reduce the natural frequency. So those rules don't get changed. They're physical rules that are always in place. So we always have to keep that in mind when we're thinking about vibe fixtures. You always have to take into consideration the mass acting upon the force sensors. This is an example done at NASA some years ago, but it just highlights a little bit about the head expander and putting force sensors, installing the force sensors. In this case, they used a 25% rule, 4 steps preload, and then did a star pattern. Fairly big ring of about 102 inches, 12 sensors, and a custom preload bolt. So this is maybe a schematic of what that might look like. And what you see here is you can easily write the expressions for Fx, Y, and Z. Also, Mx and Y would be used to compute the overturning moment, and Mz would be also something you could write as well. Again, grouping sensors around primary axes and then writing the expressions. Now, again, I just want to highlight that given you can put all the sensors into the say the M+P vibe controller, you're getting the benefit of not having to write these expressions, but simply just defining your geometry and letting the M+P vibe runner do all the heavy lifting and give you a real-time solution. Pretty powerful. Okay, so force ring preloading, again, just to go over it again, sensors are laid down on the bottom ring. We have a top ring coming down. We're then preloading per the 25% rule. We're then left with a assembled fixture, and now we have to preload, or we have to now calibrate it. So the calibration typically is done dynamically, and you're using either a low-level sweep or a dwell below the first resonance, and you're really testing the apparent mass, and you're looking at force, and you're putting an accelerometer on in the direction of the vibration, computing the apparent mass, and then you're comparing it to the actual mass that the sensors are exposed to. And that would be a function of how heavy is the ring, how heavy, and maybe you're just testing it as a vibe fixture. So you take into consideration the preload bolts, the top ring, and then you compare that mass to the mass of what you just tested dynamically. And that would give you like a calibration factor or a correction factor if you wanted to use it. If it's within a couple percent, I usually don't worry about it, but if it's off by maybe 5 or 10%, then it could be something a little more where you require a closer look. So maybe a sensor isn't hooked up right, or a bad cable, bad sensor, who knows? It could be a bad channel on the signal conditioner. It could be a lot of things. So you just want to make sure that you take a look at that when you see large deviations. It does require a closer look. And lastly, before we go to Dale, it's just a simple example of how it might look using say a vibe runner controller. You would put the sensors in front. You would have either a dynamic lab amp on the front end converting to a voltage. This would give you full rangeability selection, so you have near infinite flexibility in terms of rangeability. These would be on the X and Y channels. The Z channels would get the quasi-static one, because that's the one you want to do the preloading on. And then during the vibe test, it's a dynamic amp. So you just dial in a short time constant and you're good to go. All channels are fed into the vibe runner. The vibe runner is doing all the heavy lifting and doing all the real-time calculations to make the control work. So on that basis, I'm going to hand over to Dale. Let me stop sharing, Dale. All yours.
Thanks, Bill. So if you remember our invite here, we've got this lovely picture of this giant setup just keep this in mind, for when we go over to the actual setup for our live demo, because this situation definitely can't fit in my office, so we got a much smaller system to run here. So in this portion of the webinar, we'll be reviewing the external and software summing options. We'll be reviewing example force limiting configurations, which will include different types of notching techniques. We're going to go over a manual and automatic notching comparison, and then show an overview of our demonstration configuration so that you can see exactly what we're running, and we can talk a little bit about the preload operations and in situ calibration that Bill mentioned earlier. That'll be followed by a live demonstration, and then we'll get to review a little bit of the data which we collect from that live demonstration. So now we're going to compare the external summation, or summing with external hardware, with software summation. External summing utilizes charge amplifiers and summing junctions to reduce control system channel utilization. So in this type of configuration, each axis is summed, providing a combined output channel for each axis. Additionally, pairs of force sensors can be combined to calculate the in-axis overturning moment. So the resulted sum forces can be sent to the control system for limiting functions to be applied. So in this configuration, each of these channels goes into either a summing junction. Well, they all go to summing junctions, but as far as the z-axis goes, which would calculate the overturning moment in the vector of excitation, we would also get the overturning moment y, or z rather. External summing has the advantage of providing an independent hardware solution, which is because it calculates this outside of the controller and ultimately uses less control channels. However, the increased complexities can lead to more failure points, and individual cables must be independently verified prior to testing. Now, in the software summation, each individual channel is passed through the charge amplifier to the control system directly. As a result, individual channel limits may be applied to each axis. Now, because the software calculates the overturning moment for each sensor instead of in groups, the off-vector moments can be calculated. So if the vector of motion is directly in line with what would be the x-axis on this system, or the y-axis rather, then but the CG were slightly off, we would still calculate and limit to that somewhat off-axis center of gravity. Whereas if we had paired the sums, or summed the pairs rather, to calculate the moment, we might only see the in-axis energy, and it might obviate anything that's off-axis. Though this solution requires more hardware channels and is calculated by the same system providing the control of the shaker table, it does offer numerous benefits. Firstly, the moment calculation system can be configured with just the Cartesian coordinates of the sensors, greatly reducing complexity. So all those giant force expressions that Bill showed earlier can really be mitigated by just plugging in the Cartesian coordinates and the names of each particular sensor, and then the software takes care of the rest. Secondly, pseudo channels can be used for calculation and are only limited by the software. So groups of sensors can be summed separately. So for instance, if you had 4 dynamometers, as Bill explained, we could sum the local moments on each dynamometer and then combine those local moments into an overarching overturning moment. Lastly, the individual channel limits can warn the user if a bad cable or sensor overload occurs. So if a single cable were to go bad during a test, this could either warn or abort the system because you're not going to be limiting to the full potential of the system. And this does happen. In fact, when we did our original testing of this, there was a bad cable in the system, bringing down the overall average of the calculated force when it was calculated through summing junctions. And this was only apparent when we connected every single cable individually. So though this system would still give us a summed in-axis force, if we were able to achieve this level at the first bending moment, we probably wouldn't have limited to quite a low degree because we wouldn't have seen the full potential of the excitation. So now we're going to go through the various software configurations available for force sensors. In the control software, there are 3 options for pseudo channels of summing type. The first one is root sum square, or RSS in the software. This allows for 3-axis sensors to be mounted at off angles, and it will quantify the total energy of the sensor using a simple calculation, as shown here. Summed force, which is known as vector add in the software, is a simple weighted sum of all the sensors in the calculation. And moment, which calculates the overturning moment of the system using coordinates or weighted by distance, automatically calculates these force expressions for you depending on how your system is configured. A critical component of the force washer installation is preloading, which requires precise application of torque in segments to arrive at the correct preload. For this reason, quasi-static charge amplifiers must be used with the long time constant. And some of the charge amplifiers can be directly controlled by our control system using a USB connection. So if you were to use this, you could configure the preload sensitivity, which is often different than the operational sensitivity, and set it to a long time constant in order to achieve the preload operation. Just as important as correct preload on these sensors is the location and orientation. As forces are often summed in the time domain, opposing polarity can lead to signal cancellation. Thankfully, in the software, if one of these sensors is installed upside down, the polarity can be reversed in the software by just entering a negative sensitivity. Some forces utilize the vector add feature with a weighting of 1 per channel. So a limiting or notching profile can be entered with multiple breakpoints in order to protect a specimen. This operation can be done for all axes, and in our live demo, we will have summed force for X, Y, and Z, as well as the moment. For single plane overturning moment, you can actually still use the vector add function, but in the software, you would enter the weighting values as their distance about the moment datum, which is essentially the center of the excitation axis. And in this one, you are limited to only the n-axis energy, which is similar to doing a pairing or summing junction on the outside. To automatically calculate the overturning moment for any vector of motion, however, the moment calculation is used. And this is the one where you would enter the Cartesian coordinates about the center for the mode, but the limiting function would be applied to the true overturning moment of the system, so any off-axis CG would be captured. So prior to this type of force limiting testing, engineers had to limit the force of input by using a manual notch or shaped input profile. And here we will look at this technique of manual notching and compare it to the automatic method. Manual notching uses predicted or measured system response to change the reference profile. This is sometimes known as a bathtub notch due to its shape. It does require less equipment to execute, but I would argue that it requires a bit more pre-planning in order to execute correctly. Defining this notch requires careful analysis of the system response. In our example specimen, we've made a low-level sine sweep to determine the forces that would occur at higher-level tests. A properly designed manual notch should somewhat follow the slope of the response Q factor. So in our plot on the upper right here, we can see this rigid body mode, which is what Bill had called the usable range for a in situ calibration. And then we start to see the load or the forces deviate from the input, which in this case is 0.1 G. Wherever it starts to deviate is about where we would want to start considering entering into our bathtub notch. So you can see for this first mode, this is a much slower slope as the mode is much more highly damped. And then for the second one, this is much more aggressive. So this second one, we would probably design to be much skinnier, so to speak. And this is where we're going to consider our initial slope. Where the blue dotted lines appear is where we would flatten the bathtub to its lowest level. And though you could shape the bathtub notch more to meet the criteria of the mode, there's always examples where the mode can become nonlinear, and if the mode changes in frequency or amplitude in any direction, suddenly your bathtub notch becomes a little bit less effective. So we typically lower it out into a flat bottom so that we can capture it if it's just a few percent off. To determine the level, I've simply taken the ratio of the desired response, which is 2 pounds force, to the actual response, which in this case is 6.78 pounds force, and applied that to the input force. This method does not take into account damping, so it's oftentimes somewhat experimental. For the first mode, in this case, the value drops from 0.1 G to 0.029, as shown here. And the second mode requires less reduction and sees the input drop to 0.0438 G, but it has a more aggressive slope because it's less damped. Now we're going to run this test first during our live demo and then compare the results to a completely automatic notch. When defining an automatic notch, much less pretest analysis is necessary to determine the limit values. Though easier, it's much more critical that the sensor configuration is rock solid, as it's heavily relied upon to produce results. With a fully automatic force moment limiting notch, the acceleration plot remains undisturbed. And we can see this here with 0.1 G acceleration all the way across. Because the system will attenuate the input acceleration to limit the force based off our automatic notch profile, which is down here on the right. And I simply drew a line from the minimum frequency to the maximum frequency of our test at 2 pounds force, which is the summed in-axis force of the Z, and we're going to try to limit that to 2 pounds. And by the way, we're trying to do that in both the manual and the automatic notching cases, so we're going to do both there. These two techniques can even be combined to help catch deficiencies in the manual notch or as a safety net in case the automatic notch fails due to equipment failure. Combining the two, however, can lead to test aborts, as the handoff from one to the other is often rather abrupt, as we'll see in the live demonstration. So here we're going to review the configuration of the live demonstration so you know what it is we're running. And if you remember that giant, awesome 32, force sensor setup, well, this is our marketing versus the reality, because this little guy fits in my office and it's sitting right behind me. You can't see it because it's blurred out by the background, but this is what we're going to run today. So we have a CubeSat launch mass mockup. This is not a real CubeSat. It just has some like G10 model inside along with the 1U launcher. We have a control accelerometer, which is 100 millivolts per G, IEP. We have a force ring, and the force ring is meant to mount the test article to and then to preload the bolts on the force sensors, of which there are 4, and these are the 9028C force sensor. It's a 3-axis force sensor with 4 kilonewton capability on the X and Y and 8 kilonewton capability on the Z, which is before the preload, of course. And then we have an expander head meant to increase the test size from our small shaker armature here. Now the force washer is orientated as shown. And this is the Z-axis is normal to the shaker, so this is the one we're going to use to calculate overturning moment. And here you can kind of see I didn't use the best preload bolt. For what Bill was describing earlier with the engineered bolt and the ring nut, this would have made for a much easier installation. Because if you can imagine that I have these force sensors on the ring and they have to be expertly positioned, then you have to put the force ring on top and then load the bolts in the top. It's very difficult to do that, especially just with one person. So if I had used the engineered bolt with the ring nut, the engineered bolt would actually bolt into the expander head here on the bottom, and then it would protrude through the top. And at that point, you could set the force sensor on top, load the force ring, and all you would need to do is make sure that the force sensors aren't off axis, which, as you saw before, some customers use some clever fixtures in order to keep those in place. But all this suffice to say that I think the engineered bolt and the ring nut are probably one of the easier ways to install a system. So on the instrumentation side, or on the data acquisition side rather, each of these instruments is connected to one of these lab amps. The Force X components are all connected here. Force Y components are all connected here, and the Force Z components on this charge amp. All these outputs are then scaled 1-to-1 to the control hardware here. And this particular force amp is the one that was used in the long time constant in order to provide the preload operation. So let's run a test. I'm going to move over to our control software. And the very first test we're going to run looks a little familiar to you probably, if you remember the manual notch that we created earlier. So we're going to self-test the system. While this is providing a self-test, we can see here that we're on our components, which are being driven by these charge amps. There's a web interface to the charge amps that can actually allow me to go in and view the individual sensors, change their time constants, set sensitivities, and more. And if I close this browser window, it'll just continue to operate. So self-check is done. The self-check puts out a pseudo-random and provides a prediction for the response. So this is the accelerometer that's on top of the CubeSat. This is our in-axis force, our cross-axis force, X and Y, and these are summed. And then over here, I've got our in-axis force, which is summed Z, divided by the control channel input. And this is how we can do an in-situ calibration. So if I start running here, we're building up to 200 Hertz. I can hold the system here and then look at my cursor, and I can see I have about 8.9 pounds force, which is about the in-axis, which is about the amount of mass that the CubeSat, the expander head, the force ring, and all of the fixturing, all of the instrumentation, and even the little bit of bolt that protrudes above that expander head, or above that force sensor, which is preloaded, those all have to factor in. So if you're doing an in-situ calibration on a spacecraft, you have to think about the accelerometer cables, the umbilical cables that are coming off of your test article. Any little tiny thing has to be added to this entire mass in order to provide the in-situ calibration. So we're going through our manual notch. We can see our in-axis force was limited, but only to about 2.5 pounds, which kind of overshot my target of 2. And a lot of this is because I didn't take into account the damping calculation. And now we just have a test abort here, which indicates that there's a third mode that I didn't exactly plan for. And this kind of illustrates the importance of the pretest analysis, because if I had planned for this, or even if I hadn't planned for this, I could have had an automatic notch on there somewhere in order to capture this. And that's what we're going to do next. So I'm going to open the next test profile, which is almost the same as what we had showed before. Go, loading. This is going to put out the same self-check, but you see here, now we just have 0.1 G straight across. This is a really simple test profile. This could follow some shape for a test specification. It could be random, it could be sine. And either way, we still get the same in-axis response. Our predictions look very, very similar, except that we can see here on our in-axis force, we have this notch here that's driven to 2 pounds. So at any point, if these in-axis force calculations go above or close to 2 pounds, we are going to notch those. And we can kind of see that in action here in the lower corner. By the way, this could be cross-axis response. It could be in-axis force combined with moment, combined with some responses on the test article. And the lesson there is that whichever one takes the most error is the one which will take control. Now you can see our first mode, we've kind of cut off the mountain, so to speak, of force input, and we have a very particularly shaped notch, which is exactly what the test article calls for. This is basically slowing the inertia of the input force in order to give you a perfect test profile. Okay, so we've completed the test there, and you can see our in-axis force, we can see our Qs of the in-axis force per mode, which look precisely like they would if I had tested without any notching at all. And this is just because we are providing a transfer function from our control input into our in-axis force. And those will be really useful later. So now we're going to run a combined. notch. And so it's going to be a manual and an automatic notch, which are combined. Yes, we're going to load this. And then right after this, we can take a peek at the data that's produced from this. Okay, going to run. So what we're probably going to see here is that the manual notch is going to follow the exact same thing as it did before, but because I didn't carve it out deep enough, we're very likely going to hand over to the force limiting somewhere around the 2.5 pound mark. And here we are approaching. And here is the handoff. You can see we did cut it off there. But if you can imagine, if this tried to hand off, and you have a very large, complicated system with a lot of inertia, the acceleration input is going to be at its lowest it possibly can be on the table. But your force response is going to be at the highest it can possibly be at the table. So giving the control to the force earlier in this bathtub notch is a better idea because the signal is much, much better. Now you can see with the combined, we did complete the test. You know, we were able to catch the mode that we did not account for before when planning this manual notch. So the combined effort does a good job. But I think when it comes to comparing the results, we'll go back to our slideshow here. You can see here in blue is the automatic notch. So you can see the nice carve out there. And in red is the manual notch. All these areas shaded blue are areas where I would consider this to be an under test. So these are areas where the test article wanted to be excited. It was really headed toward that inertia, and we would have carved it out based on our force input and our analysis. However, because we had to make this large bathtub as a safety net, we've somewhat under tested that area. And then, of course, as you remember from the overtest, this is an area where we likely over tested the area by not using this manual or the automatic notch rather. This carries over into the force. This is the force input comparison without any kind of transfer function. And you can see these areas here were likely under tested and this area was likely over tested. And then you can see that carry over even into the response of the test article. This is the accelerometer on top of the test article just in the in-axis. And you can see the areas under tested here and over tested here. And that's all we have for you today. We actually are planning some in-person seminars where we will spend a lot more time on this. We're going to go over the preload operations because we'll have a solid 2 hours for Kistler and a solid 2 hours for M+P. So we're going to show you these things in person. We'll bring the same setup that we have as before. And just kind of teasing it here to let you know that we're going to do a few of them in the coming months. We'll be in Denver, we'll be in Seattle, we'll be in Los Angeles. And I will stop presenting here and I'll go over to any questions you might have. It looks like here, potential risks of having the control accelerometer mounted above the force sensors. Seems that the fixture stiffness would be critical in this setup. Do you know of any, Bill? I don't.
I think that's I think typically it's mounted on the shaker, not typically on the fixture, but I think the fixture is plenty stiff, so I think it should be just fine. But I think the best way to do it is have it right on the armature.
Yeah, and I think additionally, the only risk that I would see is if your fixture were not stiff enough and your fixture resonance has started to creep into your test range. You know, this is where doing a good FEM, doing a good modal test on your fixturing beforehand can really help to determine what's usable on the fixture. But I think if you were to control, like for instance, on my system here, I do have the accelerometer mounted, you know, very near to the force sensor, but it's really just because I don't really have anywhere else to put it. You know, it's a very small fixture, but also it is stiff enough. Both the fixture and the expander head were tested, and their resonances are well above 3 kilohertz. So if we're only testing to 2000 hertz for the sine test, it's actually, we don't start to see that fixture resonance creep in until, I don't know, maybe 2200 hertz or so. So, you know, we kind of did plan for that, and I think that's the key in that type of placement. We have another test that says they have CG acceleration limits with component responses, and their low frequency breakout models that include an FEM of the surrounding vehicle structure. What do you gain from force limiting testing versus an acceleration limited test? This is from Tyler. I think, yeah, acceleration limits are easier to implement, but I think the thing to consider here is what Bill mentioned earlier, in that the impedance of the shaker table is almost infinite. You know, this is a huge system, and it's not at all like the launch vehicle. So any way you can get that test to not overtest your test specimen, but also to more closely match the impedance of the in-flight condition is something that you'd want to consider. So, you know, although many successful tests have been done without it, using the force limiting input in order to limit can not only protect your specimen, but can protect your slip table as well when doing that kind of test. We have another question that says, is there any specific differences in implementing force limited in a sine sweep versus random vibration? Yeah, your pre-test analysis will be a little different in that you'll use random, but even if you're doing random testing as your full level random test, I would still recommend doing the sine sweep, because when you're moving in the rigid body mode, this is where you can see the force input to do your in situ calibration. So although you're doing a random vibration test, I would recommend doing the pre-test analysis and the in situ calibration using sine. And that just means your pre and post, testing would be done in sine as opposed to random. Got anything else to add, Bill?
Nope. Thank you, everyone. Had a good turnout here, so thanks very much. As there are a lot of you guys might know one of us, if not both. So just please reach out if you have any further questions.
All right. Thanks, everybody.
Bye bye now.